Hello and welcome to today's webcast brought to you by Laser Focus World. Today's event, Fundamentals of Raman Spectroscopy, will be presented by Sebastian Remy, Applications Scientist at Princeton Instruments. This presentation is both live and interactive, so you can ask questions at any time by clicking in the Ask a Question box in the presentation window and clicking the Submit button. Located in the Event Resources section below the Q&A is a PDF of today's slides. If you are running pop-up blocking software, you will need to disable it to view this webcast. In addition, it is recommended that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from our homepage at www.laserfocusworld.com. And once again, please ask questions. That helps make the end of the webcast more interesting. And now it gives me great pleasure to introduce our presenter, Sebastian Remy.
Thank you, John, and thank you everyone for attending today's webinar. So I'm application scientist with Princeton Instruments, and in case you do not know who we are a global leader in manufacturing of scientific cameras and spectrometers with offices in the US, Europe, and Asia, and distributing worldwide. And recently, we started a series of webinars illuminating the fundamentals of spectroscopy, that is interactions of light and matter. So today we will continue the series by talking about Raman spectroscopy. Raman scattering is a process where incident light interacts with vibrations of the molecules in the sample. Typically, these days lasers are used for this process, and the laser photons can either excite vibrations in a molecule and lose energy, or pick up energy from existing vibrations that are usually thermally excited. In any case, the energy change relative to the laser wavelengths of the photons can be spectroscopically detected as a color change, and it is characteristic of the sample that is being investigated. The Raman process itself is non-destructive and does not require direct physical contact to the sample. Historically, Raman scattering was only theoretically predicted in the early 1920s and first observed in 1928. So the picture on the top right shows one of the first recorded Raman spectra, and back then it was quite painful, a quite painful process that involved using filtered sunlight or a little bit more intense light of monochromatic atomic emission lamps to excite the Raman sample. As we will see, Raman scattering is a weak effect, and the light sources, or using the light sources available back in the day, you could only record a spectrum like is shown here by exposing for a couple hours. Nevertheless, the technique or the use of the technique in physics and in particular chemistry was quickly recognized, and Raman spectroscopy got more widely established quickly. However, only experts were able to handle the sensitive experiments that were needed to discover the weak signals. A big game changer was the invention of the laser in 1960, and that made Raman spectroscopy really more widely accessible. Mainly the higher energy densities, and thus increased Raman scattered photons, or made them more easily observable. Today, laser excitation covers a wide range from the UV to the IR, and all of these wavelengths are used to excite Raman processes. Also today, Raman spectroscopy is a widely used analytic technique. It's fairly easy to set up with a vast amount of applications in scientific research and industrial processes. The applications span really a wide net. So here I list a few applications ranging from material science, chemistry, physics, into the life sciences, where Raman is used to analyze biochemical processes, as well as applications in industrial environments like research, quality control, and process control in pharmaceutical and semiconductor industries. We will later see a few application examples illustrating some of the many useful properties that can be measured with Raman spectroscopy. The output of a Raman measurement is typically a recorded Raman spectrum, such as the one shown on this slide. Raman measures energy shifts relative to the relatively strong laser excitation line, and Raman spectroscopy conventionally uses units that are called wave numbers that are measured in a unit called inverse centimeters. That originates from the fact that Raman energy shift is very conveniently used because it's independent mostly of laser excitation wavelengths. However, the energy of a photon is inversely proportional to its wavelength, so that's why the inverse units. Raman shifts can be broadly classified as Stokes shifts for decreasing photon energy, so that increases the wavelength, and anti-Stokes for increasing the photon energy that decreases the wavelength. And each Raman peak you can see in the spectrum corresponds to a Raman active vibrational mode. And I want to note that not all vibrational modes have to be Raman active. So which modes are active depends mostly on the molecular symmetry of the sample. As energy is picked up from or lost to vibration modes, Stokes and anti-Stokes lines are located symmetrically around the laser line. And as vibrations are typically excited by thermal processes, the intensity of the anti-Stokes lines in particular that require vibrations to be present to be visible will decrease with falling temperature. But let's look first into some examples how Raman spectroscopy is applied and some practical considerations for its implementation. So to do that, I will first, in the next section, talk about applications of Raman spectroscopy. And then we will discuss in a section the components of a Raman system, and finally show some common experimental setups. So let's look at some applications of Raman spectroscopy. Obviously, this can't be a complete list of all applications, but the next few examples, with the next few examples, I will hopefully show you the power of Raman spectroscopy. We've seen that the peaks in the Raman spectrum are due to interactions with modes of molecular vibrations in the sample. So the Raman active spectrum of vibrations is determined by molecular bonds and symmetry, and it is characteristic for each molecule, and unique in a way that can be used as a fingerprint to identify different materials. So the figure on this slide shows Raman spectra of different hydrocarbons. And when we look at the spectra of cyclohexane and isopropyl alcohol in particular, the differences are clearly visible. However, someone might also note some similarities in the Raman lines of these two substances that can be attributed to vibrations of parts of similar structure in each of these hydrocarbon molecules. Also shown is a spectrum of mineral oil that is fundamentally of a more complex nature, as it consists of very many different molecules and hydrocarbons of very different kinds and length. Depending on the complexity or purity of any mixture or material, these days one can use computer algorithms that contain catalogs of pure spectra to quickly identify individual components. Besides material identification, one can also look for deviations from the pure Raman spectrum, and that can be effectively used to determine the purity of a material. For example, that can be used in a quality control process in the pharmaceutical or chemical industries, for example. You see a wide range of instruments used for these tasks. They are more or less complex depending on the level of sensitivity that will be required. Beyond material identification, Raman scattering is also an effective tool in doing quantitative analysis on materials. For example, to determine the mixture ratio of two substances. So here we show the individual spectra of ethyl and isopropyl alcohol as they are found in common household rubbing alcohols. The difference in the spectra is clearly visible. So orange shows the isopropyl alcohol, and the violet spectrum is for the ethyl alcohol. Now this spectrum, in this spectrum, the orange graph shows the Raman spectrum of the mixture of both solvents. And for reference, as a violet spectrum, I also show the isopropyl alcohol. By measuring the characteristic properties of the spectrum of the mixture, a quantitative value of the mixture ratio can be found. So for example, a simple approach could look as follows. One could look at the ratio of the individual peaks in the highlighted section of the graph, as these are unique to either the ethyl or isopropyl alcohol. The ratio of these peaks can be calibrated to relative concentrations of the solvents by an empirical model that's determined from intensity ratios of known mixtures. This model can eventually then be used and applied to unknown mixtures to determine the mixture ratio. The nature of the Raman process makes it a great tool for investigating the internal properties of materials. It's very sensitive to changes in molecule, lattice, or crystal structures, or the presence of defects in the molecule. Also, the interactions between the atoms in the sample can be very sensitive to the external physical and chemical environment. So understanding the influence of, let's say, pressure on the Raman spectrum makes the Raman measurement an effective sensor for pressure. In particular useful that can be in microscopic or remote observations that are not otherwise accessible by other techniques to measure these quantities. So let's look at a few examples. A great example is the study of carbon and carbon-based materials. So pure carbon can take various forms, from amorphous to various crystal structures, for example, diamond and graphite, where graphite is itself made up of stacks of monatomic, honeycomb-like layers of carbon. Single layers of graphite are called graphene, and they have been very popular material science in the past few years, so you might have heard of those. The figure on this graph shows the Raman spectra of different forms of carbon that can be clearly differentiated. So, in fact, the Raman spectrum is the most effective way to differentiate between different kinds of carbon structures. It's even possible to differentiate between single, double, or higher numbers of individual monoatomic graphene layers. In the presence of defects, carbon Raman spectra show an additional line called the D band that appears in the spectrum. So you might see there's one spectrum labeled damaged graphene where you see a peak labeled D on the very left. So the Raman lines also show characteristic shifts depending on, for example, applied stress and strain, charge doping, or chemical impurities. And in reverse, the measurement of the Raman spectrum can be used to measure any of these quantities. Consider now a situation when stress is applied to a material, for example, by stretching or compressing it. So this will lead to a stretch in the molecular bonds that will lead to changes in the energy of the lattice vibrations. And that change can be detected as a shift in the Raman bands. You can then use a calibrated measurement or modeling of your device or sample to reverse the problem to measure that quantity using Raman. So in this case, to measure strain using the Raman spectrum. So in the figure here, it looks complex, but it simply shows a measurement on a microscopic transistor that exhibits actually strain when electric fields are applied. So it shows the peak position as function of that electric field, and on the bottom right, that information has then eventually been converted using a model to the measurement of characteristic strain in the material. Today, Raman spectroscopy also finds wide use in the life sciences. So here we are coming back to graphene, that is the monoatomic layers of carbon. The figure here shows experiments that do microscopic measurements of cells that have been placed on a large sheet of graphene. The Raman spectrum of graphene is very sensitive to the chemical environment through charge doping. And so this presents now a non-destructive technique to detect the biochemical structure of the cell on a microscopic level. Specifically, here this effect is used to measure the pH value of the environment of the cell. In the Raman spectrum that is shown in the figure, one can see clear shifts between different spectra that were taken next and to and within the cell that is shown. Another interesting application of Raman spectroscopy has been the detection of cancer in cancerous tissues. Essentially, the Raman spectrum is a fingerprint of the biochemical makeup of the investigated tissue. The figure here shows research that uses a probe that can be used in a minimal invasive in vivo measurement. The setup uses optical fibers to transport laser light to the sample tissue and to collect the Raman signal and guide it to a spectrometer. The key result of these measurements is that Raman can differentiate between cancerous and non-cancerous tissues. The figure also illustrates a common problem in doing Raman on organic substances. Says that is their autofluorescence when excited by the laser. So look, for example, at the graph on the top left. The blue curve shows the raw acquired data that is dominated kind of by a broadband background. The higher resolution Raman spectrum that is shown in red can, however, be recovered after correcting the spectrum using hardware and or software techniques. For example, typically a high excitation wavelength is used. 785 nanometers is very common to minimize the excitation of broadband fluorescence that can build this background. Here's another life science application that uses SIRS probes to target different biomarkers. SIRS stands for Surface Enhanced Raman Scattering. It describes an effect when there's a massive increase in the Raman signal if the Raman active substance is close to a metal surface or nanoparticle. Shown in the figure is, on the left side, for comparison, a typical signal of a fluorescent probe compared to the Raman probe on the right. One can clearly see that the Raman signal is spectrally very narrow compared to the fluorescence. This is attractive because it allows for simultaneous, highly multiplexed measurements by designing probes with slightly shifted Raman wavelengths, depending which specific biomarker they detect. And more probes can be uniquely identified within the spectral area of detection due to the narrowband nature of the Raman lines. This requires, however, setups with very high spectral and spatial resolution. To summarize this section, we have hopefully seen that Raman spectroscopy is a very flexible and powerful experimental tool. It can be applied on macroscopic and microscopic scales, used with remote or fiber probes, and the quality of the instruments can range from simple handheld devices to big lab-scaled devices. As a measurement technique, it's very sensitive to different environmental factors. It typically requires high resolution in the spectral detection system, and it can be quite weak and requires sensitive detectors. However, it typically also requires no or very little sample preparation, and it is non-destructive. In this section, I want to talk about what components build a Raman spectroscopy system. This figure shows components that can be found in some form in any Raman system. So on the bottom left is shown a picture of a laser that provides a high energy density and monochromatic light source. In many lasers, the power can be tuned. That can be useful to switch to a high power mode to detect a lot of signal, where some samples might require application of less laser power because the sample might be sensitive to, let's say, radiative heating. The laser goes through a filter to clean up the excitation light. That filter is a very narrow bandpass around the laser line. The Raman signals are very weak, so even very low intensity features of the laser beside the main line could overpower the Raman signal. After hitting the sample, light that is collected in the collection path will go through a laser blocking filter before being detected by a CCD camera in a spectrograph. So next I want to look at some of these components more closely. In all Raman measurements, it is crucial to block the Rayleigh scattered laser light. That is because the Raman cross-sections are very low. Typically on the order of magnitude 1 to 10 million times weaker than the Rayleigh scattered intensity from the laser. So if no filters are used, the stray light from the laser would simply overpower the weak Raman signal on any detector. The good news is state-of-the-art filters easily achieve a reduction of laser line by 6 or more orders of magnitudes. And so the curves here show the characteristics of filters typically used. So notch filters block off a narrow band around the laser line, letting longer and shorter wavelengths pass through. And the advantage is that Stokes and anti-Stokes lines can be observed simultaneously when using such a filter. Very common these days are also long pass edge filters that only let longer wavelengths than the laser line pass. Besides the optical density of the filter, the transition width is an important specification of a filter. The transition width describes a region around the laser line where light is blocked and no Raman light can be observed. Typical transition widths are around 100 wave numbers or more, although special filters can reach transition widths down to a few wave numbers. The most flexible method to observe at low wave numbers are still multi-stage spectrographs, such as the TriVista from Princeton Instruments that is shown on the picture on the slide here. They allow observations really close within a few wave numbers of the laser line and don't require any optical filters. While filters are by nature limited to one specific laser wavelength, the multi-stage system has also the advantage then that it can be easily configured for multiple excitation wavelengths if that is required for the application. The spectrograph splits the Raman light into its spectral components and also holds the detector. Depending on the application, one needs to make sure to configure the spectrograph system with the right components to achieve the right resolution, achieve high throughput to detect the weak Raman signals, to configure a system that covers the desired spectral range, and a system that has a suitable sensitiveness detector for the measurement. Recently, aberration-free dispersive grading spectrometers have shown to be efficient tools for Raman measurements. Aberration-free designs like the Princeton Instruments isoplane or Fergie system can increase the signal-to-noise ratio of the measurement while maintaining high resolution. The Raman spectrum on the right, for example, shows a comparison between different spectral instruments. Essentially, lower aberrations increase the ability to more tightly focus light into less pixels on the detector. Also, grading spectrographs are very flexible in that they can be configured with a wide range of different low noise detectors. The central component of a spectrograph is the diffraction grading. Diffraction gratings are characterized by the groove density and Blaze wavelengths. The groove density essentially determines the resolution of the device, but also the spectral range that is being covered. And so it's typically important to find the right balance between spectral resolution and spectral range covered. So look, for example, to the figure on this page that shows two cyclohexane Raman spectra taken with two different gradings on the same instrument. The higher groove density grading will increase the spectral resolution, but shrink the spectral range observed on the CCD, so the spectrum cuts off earlier. I would like to note that larger spectral ranges can be obtained by using step and glue techniques, where the grading is moved to different wavelengths between acquisitions. While this takes a little bit longer time, it will also reduce the wavelength accuracy somewhat due to the inaccuracies of the mechanical grading drives. So it's important to use a high-quality spectrograph that can keep these errors minimal if a step and glue acquisition is required. The blaze of the grading determines essentially the diffraction efficiency for a given wavelength. It's essential to consider to be able to increase the throughput through the system. The good thing is many spectrographs can hold several gradings to optimize spectral range covered, resolution, and efficiency for different measurement scenarios. Another consideration when choosing spectrometer and detectors is the laser wavelengths that will be used to excite the Raman measurement. Excitation wavelengths today range from the UV to the IR, so some very commonly found wavelengths are listed here. For example, 532 nanometer sources from diode pump solid state lasers or 785 nanometer diode lasers. We talked earlier about the reverse relationship between wavelength and energy. Well, the Raman shift is described essentially by conservation of energy. Essentially, it shows a constant energy shift independent of excitation wavelengths. However, the spectrograph operates in wavelength range. To illustrate this, we show on this slide the physical extent of a cyclohexane spectrum for two different excitation wavelengths. So one can see that for and we compare this to the size of the CCD detector used. So for the shorter wavelengths, as shown on the top, in this case the signal fits well within the detector, whereas for the longer wavelengths, part of the signal would be cut off in a single acquisition. However, it will be easier to measure higher resolutions at high excitation wavelengths due to the wider spread of the spectrum. On the other hand, one can use higher groove density gradings at shorter wavelengths. So while 785 nanometer excitations are often used in organic samples to minimize autofluorescence, one has to keep in mind that the Raman cross-section increases inversely to the wavelengths to the power of 4. So it is much stronger for shorter excitation wavelengths as well. Finally, a quick word on detectors. Lab spectrographs use CCDs as measurement tools, and CCDs are very sensitive devices that typically have almost 100% detection efficiency. They are very low noise and are sensitive from the UV to the near IR. Depending on the application, the choice of a different detector might be necessary depending on how weak the signal is or how fast acquisitions have to be determined. They have to be acquired. Having seen the components of a Raman system in the previous section, let's look now at a few use cases showing Raman setups. First, let's look at the basic Raman system based on the Princeton Instruments Fergie spectroscopy system. This system here is configured to measure liquid phase samples by placing a cuvette in the sample holder shown here on the left side of the picture. This system uses pre-configured cubes that are configured for specific excitation laser wavelengths. The advantage is the cubes require minimal alignment by the user to achieve optimal results. There's a Raman filter cube that contains a dichroic mirror and a laser blocking filter, and a coupling cube that connects the setup to the spectrometer, and it's designed for the most efficient F-match coupling into the spectrometer. So a weak Raman signal is automatically collected efficiently. If more flexibility is required, we've seen that fiber-based setups can be used. Optical fibers would then transport light from the laser, but also collect the Raman scattered light. This is in particular convenient to use when it's used with a fiber-coupled Raman probe. And example of how a probe looks is shown in one of the pictures on the slide. The Raman probe itself contains all the necessary laser.
Hello, this is John. Sebastian, I stepped away for a second. Are you wrapped up? Well, it looks like we lost our audio from our presenter, Sebastian, and he will just have to dial back in. We'll get him connected in just a minute. I would like to say we already have a number of very nice questions here, probably more than I can ask. So anybody who has a question here that is not asked during the presentation, all the questions will be mailed to the presenter, emailed to the presenter, and Sebastian will be able to answer them later at his leisure. So if your question is not answered in our Q&A, then don't worry. We will get it to the speaker. So I'm assuming that Sebastian is dialing in at the moment. And I got confirmation he's dialing back in, so we will hear from him in just a second. I know that the information he's presented already is thorough enough that it makes me feel like I can build my own Raman spectrometer from it. So, okay, Sebastian, you're back. Okay.
Maybe, John, where did I disconnect? Do you know?
Let's see. It's from the slide before the current one, I think.
Yeah, I jumped just back one slide. So I was showing examples of using fiber coupling, and
I think that's where you were. Yeah.
Exactly.
Okay,
I just wanted to illustrate. Perfect. So sorry about that. I just wanted to illustrate in this slide talking about the ease of use of a fiber coupled system. Here we found a lab with already an existing confocal microscope that had a fiber port. And fiber coupling made the connection really so easy that useful spectra, as the spectrum shown here of graphite, could really be acquired within minutes of the setup. So next I talk more about microspectroscopy. We've seen examples on the previous slide and early in the webinar. Microspectroscopy allows to probe very small sample volumes with very high resolution. Efficient high-NA lenses typically used in microscopes can also really increase the Raman collection efficiency. The microspectroscopy setup can also be used with scanning optics or movable stages to automate data acquisition over larger areas. The image of this slide shows a home-built microscope setup using an isoplane 160 spectrometer. The excitation laser is connected with a fiber adapter. Often these are available from the microscope manufacturer. And the filters for the Raman spectroscopy are included, can be included in the microscope assembly. The spectrometer, as you see it here, is plugged into a side port of the microscope, and it's similar as connecting like a camera to the side port of a microscope. So using an aberration-corrected spectrograph, as in this case, this allows to even image in high quality directly through the spectrograph. So that is very helpful, for example, to precisely position the sample to where you want to investigate it. Closing the entrance slit of the spectrograph then selects a small spatial region from which the data is collected. So that's illustrated by the red line in the image here. The image here shows an example of a hyperspectral data acquisition. So where the laser is now focused to different points along the slit while the sample is being scanned. Every point under the entrance slit will be sampled simultaneously, and using a computer analysis, the sample image can then be functionally colored based on the results of the Raman measurement at each point. So it's a very powerful technique. Okay, last, I want to really thank you for your attention. I hope you gained some new insights, and I hope I could really show you that Raman spectroscopy is a very powerful measurement technique. If this technique is relevant to you, please contact us. You've seen there are a lot of system components to consider, and we are happy to help configuring the best spectrograph detector choice for your specific application. So just email us at info@princetoninstruments.com. Also visit our website. There's tons of useful resources there, like videos, app notes, links to publications, data sheets, and much more. Let me also briefly mention our new Scholars Grant Program for our 30 system, and that also includes student travel grants. If you are interested in learning more or applying for a grant like that, please visit our homepage at princetoninstruments.com/30 for more information. And with that, I want to thank you again and give it back to John for questions.
Okay, thank you, Sebastian. We're now in the Q&A portion of the webcast. So to ask a question, you click on the Ask a Question icon in the presentation window. We do have lots of good questions. I probably won't be able to get to them all. As I mentioned before, they'll all go to Sebastian, and he can answer them later via email. So the first question, is there a detection limit for impurities?
Yes, but that depends really on the setup you use. One can think of, for example, is what is actually the limit you try to achieve in your application, and then you have to configure a system that is sensitive enough. For example, if the concentration is very low, the signal can be really weak. That might require a detector that can integrate for very long times, like minutes or something like this. Also, you might need a detector that can acquire really high dynamic range, because you might want to detect features that are very small compared to indications of impurities compared to larger other Raman features. So, for example, if the signal is very weak, one might consider using a liquid nitrogen detector. So it really depends on what the current application is, and then you can choose a detector that works. So it's hard to specify a numerical value kind of out of the blue without knowing more. But there definitely is some limit.
Is the Raman spectrometer suitable for silicon compounds like complex silicates and aluminosilicates, and that is rock and clay minerals?
So I'm not personally familiar with these materials, but I could imagine, there's a wide range of materials that has been investigated in the literature, so I would recommend a literature search there. Probably for most minerals, I would say that Raman can be a very useful technique, depending what you want to do. So.
What is the expected resolution for the Raman spectrum?
So resolution depends on various factors. So of course, you saw Raman spectra are very narrow, so that means typically a few wave numbers. However, in a spectrograph, that depends kind of at what wavelengths you observe. So we saw, for example, if you excite at higher wavelengths, the Raman spectrum will be stretched out over a wider kind of spectral range in nanometers, and so that is easier. It gets easier to resolve features. So a very high resolution system, spectrograph system, can typically resolve down to the sub-nanometer range, like 0.1, 0.01 nanometers. And depending what the excitation wavelength is, that can be like 1 or even sub-1 wave number kind of range. So often so an advantage of like the grading systems is often people configure them with different gradings, for example. So you can kind of have a lower resolution grading in there for kind of more survey type measurements, where you might see, oh, I need much higher resolution, and then switch to a higher groove density grading to really zoom in on the spectrum and acquire it with higher resolution.
Okay, this next question, or actually set of a couple of questions, is from someone at a medical institution, so that might help frame the question. What is I'll just ask all the questions at once. Well, no, maybe I'll start first. What is the penetration depth of Raman?
So the penetration depth depends on the sample, really. So how opaque the sample is. Also, let's say in a medical scenario, you might specifically talk about tissue. So like visible light does not penetrate very deeply kind of into tissue, so without being kind of scattered around and being not effective anymore. So that's probably, let's say, like a millimeter, let's say, range or less. If Raman is done kind of on a non-opaque liquid, it can go like centimeters. Then I mean, I showed a picture where a cuvette with like a clear liquid like cyclohexane that really probes like a large volume and can penetrate deep. So that it's, for example, in a microspectroscopy setting that can be important, because you might want to, for a non-opaque sample, you might have an advantage selecting more lower NA objective that creates a kind of longer focus, probes a larger area, and collects more Raman signal. However, non-opaque samples, like for example the graphene samples, are really just monoatomic layers, and they are on silicon, so there's really no penetration depth at all. So you want to use like a high NA objective to collect as much light as possible from those. So it really depends on the sample you're looking at. For tissue, deeper penetration that can be achieved typically with higher wavelengths. There are certain windows where light can penetrate deeper, but it's within kind of the millimeter range or less.
And the following question to that: what challenges are there to surface analysis of a bulk sample, and what solutions can be implemented to differentiate between surface and bulk composition? It
depends maybe somewhat on the measurement scenario. So you asked about surface and bulk contributions. So for example, let's go back to graphene, because that's very neat since it's only a monatomic layer. So one can typically these samples are prepared on silicon substrate, like crystalline silicon, that has distinct Raman features. And so what one can do is you can simply position your experiment that you measure on top of the graphene sheet and then right next to the graphene sheet, so that you pick only up the signal from the bulk, and then in the other case, there's something on the surface. Also, depending how opaque the material is, if you use a very high NA objective in microspectroscopy, for example, the focal depth that is created is very shallow. So by changing just the focal position of the sample, you could switch between surface and then different layers of detection in the sample. Best for those are probably confocal measurements that really where you have an additional pinhole in the signal path that really locates the measurement volume in 3 dimensions. So that's probably the most efficient way, and by scanning your sample in X, Y, and Z, you can then really pick specific regions from bulk or surface for your measurement.
What are some typical integration times?
So these days, since you have kind of these high-power laser sources, you can really access a wide range of measurement times. So also depends on the sample. Like these hydrocarbon spectra I showed are very good Raman scatterers. So you might only need like 10 to 100 millisecond kind of integration times. For weaker Raman spectra, it's not uncommon that you do 10 to 30 minute integration times even. What I didn't cover at all here is in this presentation is that there are also like time-resolved, like ultra-fast techniques that probe like Raman effects on the micro or nanosecond timescale or below that. That would go way beyond the presentation. But kind of Raman spectroscopy is set up as shown in this presentation can really go between milliseconds to hours, I want to say almost.
Hmm. Okay, we have time for, I would say, 4 more questions. Is there any particular reason why 1550 nanometers is not commonly used?
Yeah, so 50 nanometers is deep in the IR. So common like silicon detectors that are very efficient and low noise are not usable in this range. So silicon gets simply transparent above 1100 nanometers. So one has to use other detectors, for example, indium gallium arsenide detectors that are much less sensitive. So there are other techniques also in this area. If you go to the IR, you might, instead of a dispersive instrument, have something like a Fourier transform Raman technique or something like this. They would also have to use like indium gallium arsenide type detectors. So they have just much lower noise essentially to silicon. So that makes the acquisition more challenging. Specific, we would have to see a specific application. That's when we talk to researchers. That's our first question we always ask. What is your specific application? And then we can determine the right detector choice, really. So. Okay.
How small of a sample can be analyzed? For example, can you analyze an individual 10 nanometer particle?
Yes, so in particular with microspectroscopy, you can focus down to really small volumes. If you look really at small particles, let's say they're spread out on a surface, if the density is very low, you will get, that's commonly done, that you look at also little quantum dots that are on the nanometer scale, and the density of them is just so low that you can, like the fractional limited focus on a microscope is typically on a couple of hundreds of nanometers. But if the density is low, you can always position your sample that only one structure is within the focus. So a single quantum dot or single carbon nanotubes have been measured individually as well. The other thing is you might want to, like for example in the SIRS technique I showed, where you have functionalized kind of nanoparticles. If you detect the Raman signal and you have different ones kind of in vicinity, and you detect the Raman signal at a certain wavelength, you know it must be coming from a certain nanoparticle that's located on a surface. So yes, in certain scenarios you can measure volumes this small.
Okay, 2 more questions. For Raman spectroscopy, do you recommend holographic or ruled gratings?
So typically we say that holographic gratings might be a little bit better. They have a little bit less kind of stray light contributions. We would probably, ruled gratings are okay as well. We really look at the individual application and see which grading makes sense. If there's a holographic grading available that provides the efficiency and spectral range and resolution required, then great, we would choose that. But otherwise, a rule grading you will be fine too. There's really just a small difference between those in these dispersive systems.
Mm-hmm. And last question, is the sample for Raman spectroscopy in a solute, or can it be measured in situ?
Either way. Either way. I showed, for example, these cancer type of measurements. They are actually really done on, and it's kind of like an in situ kind of experiment or in vivo experiment, kind of on a living organism. If you want to really measure in situ on a sample, you might also require maybe higher speeds. The same is true if you do kind of a scanning application. Let's say you do a confocal spectrometer, you want to scan area on a surface at many points. You need to work with rather short dwell times, probably, to keep the observation time to a human possible kind of limit. So there are detectors. Specifically, we would, let's say, for example, use an EMCCD that can run faster and kind of manage the higher read noise and a faster acquisition to still acquire data in that scenario. So, yeah.
All right. Well, thank you, Sebastian. Would you like to make any closing remarks?
So yeah, I hope you enjoyed the presentation. Raman spectroscopy is really a wide field, so we could only dive into some of the like really fundamental things. And many, I'm sure in many parts, one could even get more technical or provide more detail. The good news is there's tons of resources online as well, in particular also on our website. So please get in touch with us if you have a specific question. Also, watch out for another webinar announcement that will happen in September. So it's still a little while, but it's some point, probably a few weeks before, you will get an announcement where we continue this series of fundamentals of spectroscopy. And with that, thank you very much.
All right. Well, on behalf of Laser Focus World and Penwell Corporation, I would like to thank today's speaker, Sebastian Remy of Princeton Instruments, for today's presentation, Fundamentals of Raman Spectroscopy. This presentation will be archived within 24 hours and can be reached from our homepage at www.laserfocusworld.com. A reminder email message will be sent to all registrants, complete with a direct link to the archive. We thank you for joining us today and look forward to serving you with future webcasts.